The solution of the differential equation for yt, which is given as d2y by dt square minus y, is equal to 2 cos hyperbolic t, subjected to the initial condition y at t is equal to 0 is 0 and its first derivative at t is equal to 0 is also 0. Now here the differential equation in term of the operator d can be written as this d square minus 1 into y is equal to 2 times of cos hyperbolic t, which is obtained by substituting d by dt is equivalent to the operator d. Now from here the auxiliary equation can be written as, by substituting d is equal to m, we can write it as m square minus 1 is equal to 0. Now the root of this auxiliary equation can be obtained by solving this quadratic equation, which gives us this m is equal to plus minus 1. From here we notice that these roots are the real and different. Therefore the solution of this differential equation, the complementary function, can be written as, which is equal to, this complementary function is equal to the c1 into e to the power t plus c2 into e to the power minus t, where c1 and c2 are the arbitrary constant. Now for the particular integral we write it as 1 by fd, where f of d is equal to d square minus 1 into the right hand side of this given differential equation, that is 2 times cos hyperbolic t. Now this cos hyperbolic t can be splitted into the exponential term like this 1 by d square minus 1, and this cos hyperbolic term is written as e to the power t minus e to the power minus t divided by 2. Now on solving this term, this cancelling this 2 with this 2, we can write it as 1 by d square minus 1 into e to the power t minus 1 by d square minus 1 into e to the power minus t. Now from here we notice that we have substitute here d is equal to a. Here a is the coefficient of this e to the power t. Here this a is equal to 1. Now if we substitute d is equal to a, then this term goes to the infinite, as this d square minus 1 goes to the 0. Therefore we take the derivative of this by multiplying this independent variable t here, then we can write it as t into this derivative of this denominator here written as 2 times of d into e to the power t. Similarly for the next term we can write it as t 1 divided by 2 times of d into e to the power minus t. Now substituting this coefficient of this t again in the place of d, we can write it as this particular integral is equal to t divided by 2 into 1. 1 is the coefficient of this t into the which is on the exponential, and similarly in the next term t into e to the power minus t divided by t, which can be written as this t by 2 into e to the power t minus e to the power minus t. Now applying the first boundary condition that this y is 0 at 0, before this we have write as the complete solution. The complete solution can be written as the complementary function plus particular integral. Therefore the complete solution is written as c1 into e to the power t plus c2 into e to the power minus t, which is the complementary function, plus the particular integral is obtained as above. This is t by 2 into e to the power t minus e to the power minus t. Now this is our complete solution or the final solution. Now substituting at t is equal to 0, this will give us this complete solution is equal to 0, and this say complete solution is y here. Therefore we can write it as 0 is equal to this C1 into e to the power 0 this term become 1. Similarly for the C2, this exponential term become 1, and putting t is equal to 0 here, this term is become 0, and from here we can obtain that C1 is equal to minus C2. This is equation number 2. Now taking the derivative of this complete solution, we can write it as this y dash at t is equal to, we can write it as the C1 into e to the power t minus C2 into e to the power minus t. Now the derivative of this function can be written as like this, plus t2 by 2 into e to the power t minus e to the power t divided by 2 plus e to the power t divided by 2 minus e to the power minus t divided by 2. Now substituting t is equal to 0, this derivative become as this term from here is only the C1, and from here this is C2, and this all these term are multiplied with this t, and this e to the power t by 2 is cancelled with this e to the power t, and both are term are multiplied by t, therefore this term are 0, and hence from here we obtain that C1 minus C2 is equal to 0. Now solving equation this C1 and C2 simultaneously, we obtain C1 is equal to C2 is equal to 0, and hence the final solution we can write it, and from here the final solution can be written as this y is equal to, by substituting the value of C1 and C2 are 0, therefore we can write it as t into e to the power t minus e to the power minus t divided by 2. Now this exponential part can be written in term of the sine hyperbolic t, therefore this can be written like that, which is correspond to the option D, and hence option D is the correct option. The solution to the differential equation dy by dx is equal to minus x by y plus 1 are a family of. Now the solution of this differential equation is obtained by a variable separation technique. Here this equation is given as dy by dx is equal to minus x by y plus 1. On using the separation of variable technique, by separating this variable dx on the right hand side and dy on the left hand side, then we can write it as like this: y plus 1 into dy is equal to minus x time of dx. Now integrating on both sides, we can write it as this become y square by 2 and plus y, then on the right hand side it become minus x square by 2 and some integrating arbitrary constant, that is k. Now on multiplying 2 on the both side of this equation, we can write it as this y square, and taking this x square on the left hand side, we can write it as plus x square plus 2 times y is equal to 2 times this arbitrary constant k, which can be further written as a new arbitrary constant c. Now to complete this y square we can write it as this x square. Now we rewrite here this x square plus 2y is equal to c. To make the complete square of this y, we can add here the coefficient of this y and its half square on the both side of this given equation. Here the coefficient of 2 and its half is 1, and we add the 1 square here in this side, and also 2y is already present here, and this 1 square on this right hand side. Then this equation become as the complete square, and we can write it as x square plus y square y plus 1 whole square is equal to c plus 1. 1. This equation is the equation of circle where the center of the circle lie at 0, and from here 0 and minus 1, and the radius of the circle can be given as the square root of c plus 1. This is the radius of circle. Now the radius of circle depending the value of this arbitrary constant c, therefore the whole family of circle can be represented here. This is suppose x is equal to 0 and y is equal to minus 1. Here is the center of the circle, and depending upon the value of the c, if the c is 0, then this circle become like this, and if c is greater than 1, then this circle become more and more larger like this. This is all depend upon the value of c, and hence this equation leads to the family of a circle, which is correspond to the circle with different radii, because this radii change with the value of c, as here c is the arbitrary constant. The solution of the differential equation d2y by dt square minus y is equal to 0 subjected to the boundary condition y at 0 is 1 and y at infinity is 0 is given by which of the following option. Now solution. Now this given differential equation can be written in the operator form as by substituting d by dt is equal to dt, and then this differential equation in the operator form can be written as this d square minus 1 into y is equal to 0. Now from this differential equation we can write here the auxiliary equation, which can be written as by substituting d is equal to m, then this m square minus 1 is equal to 0, and from here we got this m is equal to plus minus 1. Now the value of the m is plus minus 1, which are the two different real root. Therefore the solution of this differential equation can be written as y is equal to c1, which is some arbitrary constant, into e to the power t plus c2 into e to the power minus t. Now applying the first boundary condition, that is given as y at 0 is equal to 1, substituting the t is equal to 0 in the above solution, we can write it as this 1 is equal to c1 plus c2. This is equation number 1. Now again substituting the second boundary condition, that this y at infinity is equal to 0. Now putting this t is equal to infinity in this solution, we can write it as c1 plus c2. And now solving this c1 and c2, this equation 1 and equation 2, we can write here as this. We can write it as c1 is equal to 0 but c2 is equal to 1. Now the final solution of this differential equation, by substituting the value of this arbitrary constant, we can write it as y is equal to e to the power minus t. Now this solution does not match with any of the option, therefore we need to convert this exponential into the some hyperbolic or some circular trigonometric function. Now for this we know that this cos hyperbolic x is equal to e to the power x plus e to the power minus x by 2, which can be written as in two terms like this. Now similarly the sine hyperbolic x can be written as e to the power x by 2 minus e to the power minus x by 2. Now subtracting these two equations, we can write it as this cos hyperbolic x minus sine hyperbolic x is equal to e to the power minus x. For t, we can write it as e to the power minus t is equal to cos hyperbolic t minus sin hyperbolic t, which is correspond to the option B, and hence option B is the correct option. A function yz satisfies the ordinary differential equation y double dash plus 1 by z into y dash minus m square by z square into y is equal to 0, where m is equal to 0, 1, 2, 3 like that. Then consider the for statement PQRS given below. Here the P statement is this z to the power m and this z to the power minus m are the linearly independent solution for all value of m. Also, the Q statement is z to the power m and z to the power minus m are the linearly independent solution for all value of m but the positive. And the R statement is that this L and Z and 1 are the linearly independent solution for m is equal to 0. And the S is say that this Z to the power m and this L and Z are the linearly independent solution for all value of m. The correct option for the combination of valid statement is here the differential equation is given as this y double dash plus 1 by z into y dash minus m square divided by this z square into y is equal to 0. This is our given differential equation. Now this differential equation can be reduced into Euler-Cauchy differential equation by multiplying z square, and this way this we can write it as this z square into y double dash plus this z into y dash minus this m square into y is equal to 0. This is our differential equation. Now in this differential equation we substitute that this z into y dash is equal to say the operator d, and this z square into y double dash is equivalent to the operator d into d minus 1 here. Then this equation 1 can be written in the form of this differential operator d like this d into d minus 1 plus this d minus m square into y is equal to 0. This is our equation in the differential operator d form. Now from this differential operator d, we substitute this d is equal to capital M to obtain the auxiliary equation, and from here the auxiliary equation can be written as this m square minus m plus this small m plus this capital M minus this square of this small m square is equal to 0. From here we can write it as this m square minus this small m square is equal to 0. This is our required auxiliary equation. This is our auxiliary equation. Now we consider the case now. If the first case that if m is equal to 0, then from this auxiliary equation we can write this m square is equal to 0, and from here we can say that our root is m is equal to 0 and 0, and then the solution become like that. This can be written as the solution is like that. Say this y is equal to c1 plus this c2 into x, and in the this x is replaced by this ln of z, and this is our solution if this m is equal to 0, this small m is equal to 0, and which is correspond to the option that R say that if the arbitrary constant are chosen, that this 1 means this c1 is equal to 1 and this c2 is equal to 1, then this ln z and this 1 are the two independent solution for m is equal to 0, and hence from here we can say this R statement is the correct statement. Now we are looking the case for which m are not equal to 0, but these are the positive or the negative value. Then how we can deal in this situation? here I can write our auxiliary equation again. That auxiliary equation is this capital M square minus this small m square is equal to 0, and for that is the first case. For m is equal to 0, we have to obtain that this y is equal to c1 plus c2 into ln of z. Now taking the value of c1 and c2 equal to 1, then we have obtained that this y1 is equal to 1 and this y2 is equal to ln z are the two independent solutions for m is equal to 0, and according to which this R statement is the correct statement. This is our conclusion from the case first. Now in the case second, if we consider this m square is positive and also of course this is not equal to 0, then we can obtain from here this capital M square is equal to this m square, and this m square is positive, and from here we can write it as this m is equal to this plus minus m small m from here, and here the root are the real root and of course the different value, and from here we can write is the solution like that c1 into e to the power m into x, but x is replaced by ln of z, that this is equal to e to the power m into ln of z plus this c2 into e to the power this minus into m minus m into ln of z. Now these two solutions can be written like that this c1 into e to the power ln of z to the power m, and this e and ln are cancelled out, and therefore from here we can write it as this z to the power m, and similarly for the second we can write it as e to the this z to the power minus m, and from here we can see that this z to the power m and this z to the power minus m are the solution when this m square is greater than 0. That means this m is positive, which is correspond to the statement q, and this q statement is say this z to the power m and this z to the power minus m are the linearly independent solution for all value of m but positive. From here we conclude that this q statement is the correct statement. Now we are looking the case 3. In case 3, that if this m square is less than 0 means this negative, then from the auxiliary equation we obtain this m square is equal to this minus small m square, and from here we can write it as the root m is equal to plus minus iota small m, and if here the root are the complex here, then the solution can be written as y is equal to c1 into cos hyperbolic mx. This is the cos hyperbolic m and x, but x is replaced by this ln of z, and similarly the second term is written as c2 into this sine hyperbolic, and of course here iota is also iota time c2 into sine hyperbolic m into ln of this z, and from here we can simplify that this can be written as this c1 into this cos hyperbolic, and this term can be written as ln of z to the power m, and plus iota time this c2 into sine hyperbolic, this can be written as ln of z to the power z to the power minus m here. Of course here is the minus sign, and then from here we can say the root are the cos hyperbolic terms and the sine hyperbolic terms which are not correspond to the any of this statement PQRS, and from here we can conclude that only this R and this Q statement are the correct statement, which is correspond to the option C, and the C option is the correct option. Consider the linear differential equation dy by dx is equal to x into y. If y is equal to 2 at x is equal to 0, then the value of y at x is equal to 2 is given by which of the following option. Now here the linear differential equation is given as dy by dx is equal to x into y. This equation can also be solved using the variable separation technique, and we can write it as using the variable separation technique. Then this equation is written as like this, this dy by y is equal to x times dx. Now integrating on both sides, then we can write it as ln of this ln natural logarithm of y is equal to this x square by 2 plus ln of this arbitrary constant c. Here the arbitrary constant is adding in term of the logarithmic, because in this solution here one term is the natural logarithm. Therefore we add the arbitrary constant in term of ln c. Now from here we can write it as this ln of y minus ln of c is equal to x square by 2, and on further this can be written as this y by c is equal to e to the power this is 2 e to the power x square by 2 here. Then the final solution y can be written as c into e to the power x square by 2 here. Now applying the first boundary condition, that at x is equal to 0 this y become 2. Therefore on substituting y is equal to 2 at x is equal to 0, then e to the power 0, and from here we can write it as c is equal to 2, and hence the final solution can be written as by substituting this arbitrary constant value as 2 into e to the power x square by 2. Now we have also find the value at x is equal to 2 of this y, then putting x is equal to 2 in this final solution of this differential equation, that is 2 into e to the power 2 square by 2, that become 2 into e square. Now the e square can be written as 2.72 square, which is comes to be 5.111 for approximately here. Or this value can be written as instead of calculating the final value, the y can be given as e to the power square, which is correspond to the option D, and hence D the correct option.